far we have talked about modulation and everything, we have talked about on off keying and amplitude shift keying. The question is, how do I come up with an optical transmitter to basically implement this one, right. So, how do I come up with an optical transmitter to implement this one? That would be the question that we are going to answer now. What do I need to obtain the optical transmitter? What are the elements that I already have discussed? I know what a laser is. Laser is equivalent of a signal generator, right. Its output will be some power Ps and it will be e to the power j omega st. This is the complex way of writing the signal or the complex notation. The actual waveform that you are going to get from the laser, from an idealized laser like this, will be cos omega st, where omega s will stand for the signal frequency. Okay. So, this is the output of the laser. Now, this output reminds you of the carrier part, but I do not have the amplitude part. That is where we have discussed the optical transmitter called as MZM, a dual drive Mach Zehnder modulator. We have studied the characteristics of this. To briefly recall, the power transfer function goes like this. It would be a cos pi v of t or u of t divided by 2 v pi, sorry, cos square pi v of t by 2 v pi. This is the power transfer function for this particular MZM, right. Now, if I can somehow operate in only these two regions, right. So, I can operate in this region and in this region, I will be able to transmit the signal or block the signal. So, what is signal? Signal is the output from the laser. So, I have a laser, okay. I have a laser, this is my laser which is producing an output which is square root of Ps cos omega st. So, write it down, square root of Ps cos omega st, and if you take this one, connect it to an MZM, right, and then to the MZM you give, after shaping the sequence whichever that you want to transmit, the sequence is Bn, this sequence Bn goes through the transmit filter g of t and then goes to the MZM. This sequence B of n goes through g of t, generates g of t minus nt multiplied by Bn summed over all n, then this should go to the MZM, and what you get as the output will be the transmit signal S of t. So, this transmit signal S of t can be written as square root Ps cos omega st and then multiplied by this sequence Bn g of t minus nt. Is that okay? So, this is the signal that you are getting. In place of square root of 2 you have square root of Ps, but if you can kind of scale up the square root of Ps into square root of 2 Ps, then everything will be alright. Okay. So, this is the implementation that we were looking for in the optical transmitter, which would correspond to on off keying or amplitude shift keying. Of course, I have not yet completely specified how to construct this modulator because I have not told you how to bias this MZM. So, I have not told you how to basically complete this on off keying part because I have not told you how to bias the Mach Zehnder modulator. Where should I bias the Mach Zehnder modulator? I need to get full transmission and I need to get zero transmission. To get zero transmission, I have to operate this at V pi, because if I operate this at V pi, then I have cos square pi. If V of t is equal to V pi cancels from numerator and denominator, I get cos square of pi by 2, which is equal to 0. If I operate at 0, I get full transmission. Okay. So, I can bias this Mach Zehnder modulator. If I get Bn is equal to 1, which corresponds to An is equal to 0, right, then I have to choose the amplitude of this pulse in such a way that is this amplitude g of t in such a way that I get full transmission, that is I should get 0. If I get Bn is equal to, so for An equal to 0 I should get full transmission. Let me just go back, there is small confusion here. So, we have considered An is equal to 0, Bn we will have a transmission. Okay. So, we will have a full transmission here. So, I need to send in a 0 here. For Bn equal to 0, which corresponds to An equal to 1, I need no transmission, right. So, I need to send in an amplitude of V pi. The simplest way I can do this is, instead of connecting this Bn, right, what I can do is I can take this An, right, I can take this An, which is the sequence that I already obtaining, okay, and do not do the conversion factor. Rather, I multiply the amplitude of g of t by V pi and then send as input to the transmit filter. This is the transmit filter or just a pulse shaping filter, okay. To this, instead of sending Bn, I straight away connect An. Now you see what happens when An is equal to 0, the output of the filter will be 0 multiplied by V pi, that is 0, and then goes to the MZM. If the input voltage to the MZM is 0, you will be operating in the maximum transmission point or full transmission point, and what you get is the connection between laser and the fiber. So, if for example I put a fiber here, then laser will be connected to the fiber here. On the other hand, when An is equal to 1, the amplitude of the signal going into the MZM will be V pi, which means that you will now be operating at the minimum transmission point and you get 0 at the output. So, this is the way in which you can realize this on off keying or amplitude shift keying, right. Now, you might also say, is there a way to increase more number of amplitudes, or utilize more number of amplitudes? Rather than switching between symbols say 0 and 1, can I switch between symbols which we will call as symbol 0, symbol 1, symbol 2 and symbol 3. There are 4 symbols now. My alphabet includes 4 letters, right. The size of my alphabet is 4 essentially, and I want to change the amplitudes that would correspond to 4 different levels. Earlier I was changing the amplitude corresponding to 2 different levels. Now I would like to change the amplitudes corresponding to 4 different levels. It is certainly possible. All you have to do is go to the transfer function of the MZM, and then instead of operating at 2 levels, which was corresponding to full transmission and 0 transmission, you can introduce additional 2 levels here, okay. And whenever you get a symbol 0, you transmit it full transmission, you get a symbol 1, you transmit this waveform, or you operate the MZM at this point. For symbol 2 you operate here, and for symbol 3 you can operate here, okay. What would be the corresponding values that you have to verify? This is V pi, this is 0. One way of finding out this one would be to, one way of finding this is to ask how much transmission is required, right. So, this is full transmission, which is the transfer ratio of 1, this is 0. Let us say this 1 should correspond to, or let us say this symbol 3 corresponds to 0 transmission, symbol 2 corresponds to say 33%, and then this would be say 67%, and then this would be approximately 100%. Now, how do I obtain 33% transmission? I simply go back to this expression cos square pi V divided by 2 V pi, and then say this value should be equal to 0.33 for 33% or 0.67 for 67%, and it should be equal to 1. For 1 you know what is the value. So, find out what should be V by inverting this relationship, right. So, what you have to find is pi V by 2 V pi must be equal to cos inverse of square root of 0.33 cos inverse of square root of 0.67, right. The corresponding value of V will be multiplied by, so this entire thing must be multiplied by 2 V pi divided by pi. So, you need to multiply this one by 2 V pi divided by pi, okay. So, find out the values corresponding to 0.33 and corresponding to 0.67 transmission ratios, okay. I will leave this as a exercise to you, a simple exercise that you can do it by a calculator, okay. This way in which we have used multiple levels for shifting the amplitude or changing the amplitude is called as MASK, okay. It is called as M-ARRY ASK, where M stands for the number of symbols. This would be 4 ASK in this example, okay. Now, if I want to convert this 0, 1, 2 and 3, now you can think of this as a mini English language which has A, B, C and D, and for each A, B and C I can actually obtain the binary representation, okay, in terms of 0 zeros and 1 ones. I might for example call this as binary sequence 0 0, this I would call as 0 1, this would be 1 and 0, and this would be 1 and 1. Please note the inverted commas, these are the symbols. What we are essentially trying to do is taking this larger alphabet and then representing each of the letters in the larger alphabet by this smaller sized alphabet. Okay. The corresponding bit sequences could be 0 0, 0 1, 1 0 and 1 1. Okay. In optical communications, finding more than 4 levels of amplitude shift keying is kind of difficult, because the symbols start to group very close to each other, and when symbols are very close to each other, after they have transmitted through the channel, to separate them out and detect them correctly is a big headache. We are going to talk about that receiver headaches later on, but you can kind of take it from this one that practically getting more than 4 ASK is quite difficult unless you are very rich to invest in very high end products for optical communication links. Okay. Now, we have talked about varying the amplitude. Now, a sinusoidal carrier also has a phase with respect to some reference phase, and it also has its frequency. Is there something that we can change in terms of phase and frequency in order to convey the information? And the answer is yes. You can change the frequency, you can change the phase. These two corresponds to phase modulation and frequency modulation. It is not just at that point. You can combine amplitude and phase in general. You can combine amplitude, phase and frequency, but that is kind of very complicated modulation technique. But you can combine amplitude and phase. This is called as AM/PM combination, or sometimes called as, or more commonly called as, quadrature amplitude modulation. You are changing both amplitude as well as phase of the sinusoidal carrier depending on what waveform you want to transmit. Okay. So, these are all the different modulation techniques with which you can play around for a single carrier. Okay. For a single carrier, you can change its amplitude, phase, frequency individually, or you can change amplitude and phase together to form what is called as quadrature amplitude modulation. And finally, optical communications allows you one more degree of freedom, because electric field can be polarized in two orthogonal ways, in two perpendicular ways. It can be polarized horizontally or it can be polarized vertically. You can impose modulation on separate polarized components. I can transmit the horizontal polarization into the fiber, vertical polarization into the fiber, both at the same frequency, and have different modulations on both of them. So, you have how many degrees of freedom? You have polarization degree of freedom, you have amplitude, phase, frequency, and combined amplitude and phase. Okay. So, these are some of the advantages of going to optical communication, that you will start getting lot of higher degrees of freedom. So, you get lot of degrees of freedom to implement your modulation techniques. So, let us learn a little bit about quadrature amplitude modulation, and in order to do that one, I would require to introduce to you what is called a signal constellation. Okay. I know that this S of t, which we had written down, the passband signal, can be written as, so I will revert to using AN rather than BN. Okay. This mapping was little awkward in the ASK case, but it is quite straightforward in the AM, PM or the QAM cases. Okay. So, we will revert to the situation where we were representing the data sequence as AN, right. If I now take this data, square root of data AN, and then multiply that one to the carrier. So, I had written down this expression, right. So, N, you have AN G of t minus NT. Okay. If you focus on only one symbol at a time, then the signal can be written as square root of 2 AN. This is the nth time slot signal. So, square root of 2 AN G of t minus NT cos 2 pi FCT. Okay. It turns out that if you look at the spectrum of this, you will see a spectrum which is centered at Fc. Okay. But if you also look at the spectrum, this spectrum will be symmetric about Fc. Okay. Because this spectrum will be symmetric about Fc, right, with the spectral shape determined by this G of t. Okay. What you can see is that the information contained in both sidebands is completely redundant, right. Whatever the upper sideband is telling you, its mirror component is the lower sideband. So, why do I have to keep two sidebands in order to convey information? or equivalently I have spectrum centered at plus Fc, I have a spectrum centered at minus Fc, I do not require both of them to be getting back to the original signal. I can in fact multiply this one by the phase splitter that we talked about, whose transfer function was phi of f in the form of a unit step function, eliminate this one and then retain only the upper side band, right. So this kind of a modulation is called as SSB modulation, which is single sideband modulation. This is used to improve the utilization of bandwidth. Okay, this will be the way in which you can cut down the bandwidth requirement. So you have this SSB modulation. An entirely different approach is to basically write down S of t in this fashion. I will write down and then motivate what I mean by this. Okay. So I am again focusing on only the nth time slot. Okay. In fact, if you want to find out the overall waveform, then you have to sum it over all possible values of n, transmission through the from n equal to 0 to n equal to infinity. For the nth time slot, of course, this can be written as cos 2 pi fct. I have changed the notation here. If you observe, this is an, this is ani, because I want to introduce one more signal, which is g of t minus nt sin 2 pi fct. What is the advantage of doing this? Well, if you do not have the second term, the one that is sin 2 pi fct, you are transmitting something at fc, okay, and you are utilizing the spectrum. However, if you realize that cos 2 pi fct and sin 2 pi fct are actually perpendicular to each other, right. How do I say two waveforms are perpendicular to each other? If their inner product vanishes, right. So you can take this as an exercise and do it for yourself. Show that if you were to integrate this, this is the inner product. Remember, this is the inner product of cos function and the sine function seen from the previous module. So if you find this inner product and if you satisfy that fc of t is equal to some integer multiple of 2 pi, and m can be very large quantity, it can be some 20,000, it can be some 30,000, does not matter, as long as this fc of t is very either exact multiple of 2 pi or it is very large, then this inner product essentially is equal to 0, because cos and sine are phase reversed signals, I mean phase shifted signals, their areas will cancel out each other and then you essentially get up 0. So in that sense, these two are perpendicular signals, they do not interfere with each other, right. If you remember, we had written down the real passband signal S of t in terms of the complex baseband signal S bar of t or S tilde of t, and then we had said if you want to obtain from the complex envelope to the real waveform, you multiply it by e power j 2 pi fct, take the real part, also attach this root 2 in order to normalize the energies of passband signal, real passband signal and the complex baseband signal. Okay. So this is a complex signal. This complex signal can be split up into Si plus j Sq of t, okay, the so called in phase and quadrature components, and then you can write down S of t by, after taking the real part into this expression, what you get is square root of 2 Si of t cos 2 pi fct minus square root of 2 Sq of t sin 2 pi fct. Okay. These Si and Sq signals will be orthogonal to each other. Okay. Now what you can observe from this equation and in this equation is that in place of Si of t, I have ani g of t minus nt, in place of Sq of t I have anq g of t minus nt. So it is possible for me to combine this expression for S of t in the nth time slot and make it look like this complex envelope, or equivalently if I find what is the complex envelope for this signal, for this S of t signal, the complex envelope will be ani plus j anq times g of t minus nt. I am assuming that both in phase and quadrature signals are shaped by the same filter g of t. Okay. So this would be the complex baseband signal. This is the complex baseband signal, not the real baseband signal. It is complex because there is a j term sitting here, right, and as I said, this will be the exercise to you, you can show that this is indeed true. So what we have done is that we can further write this one and call this as the complex symbol an times g of t minus nt. So, the complex baseband signal what we have is essentially a complex signal, because this an bar or an tilde denotes the complex number, and this complex number can be plotted in the rectangular coordinate system, right. I can plot this in the rectangular coordinate system in the I and q axis. What is the I axis? I axis is nothing but real part of an, complex an, q is nothing but imaginary part of complex an, right. Such a plot is called as a constellation plot, or simply called as constellation, or sometimes called as signal constellation. Okay. Let us now look at some examples of this signal constellation and then discuss how can we implement optical transmitters for this. Okay. As an example, I will consider this complex symbol sequence. An can be any of these. It can be plus b, it can be plus jb, it can be minus b, or it can be minus jb, where b is some number, it is a constant. Okay. This an bar is this particular set, it can be any of these numbers. Clearly, if this is plus b, then what you are writing here is ani, anq. You can write down this ani and anq for plus b. If the symbol is plus b, right, then ani will be plus b and anq will be 0, right. For plus jb, this would be 0 and this would be plus jb. For minus b, this would be minus b and this would be 0, and for minus jb, this is 0 and this is minus jb, right. So, the way we have written down here, or rather sorry, for a and q we have to remove the references to j here, right. So, j comes in because ani plus j and q, not because j is sitting here. Okay. So, this would be b, this would be minus b. Okay. Is that fine? So, you have this complex symbol an which can take one of 4 possible combinations. So, in other words, my alphabet size is 4. Okay. And let us write down this s of t here. Okay. Let us complete what would be this s bar of t here. Since s bar of t is an g of t minus nt, there is one more way of writing the same thing. I can convert the rectangular form of an into the polar form. For example, if I have this as the complex number an bar, I can specify the length of this arrow or the line segment and specify the angle here theta n. So, I can write this as Cn e to the power j theta n g of t minus nt. Substituting this into the expression for s of t here, the real passband signal, what you get is square root of 2 real part of Cn e to the power j theta n g of t minus nt e to the power j 2 pi fct, right. So, you can combine these terms here and see that this can be written as square root of 2 Cn g of t minus nt cos of 2 pi fct plus theta n. What is Cn? Cn is square root of an I square plus an q square, whereas theta n is the phase angle which is given by inverse tan of anq by ani, right. This is the simple rectangular to polar conversion formulas that you know from your earlier courses. So, what we have are different representations for s of t. If you do not want to refer to the cosine signal or the carrier waveform, you can follow this simple complex baseband representation or the complex low pass representation in terms of rectangular or in terms of polar. You can also represent the same signal in terms of this real part of something, or you can simply represent this in the real waveform, wherein you are changing the phase of the cosine carrier as well as altering the amplitude by multiplying it by Cn. So, this form is the general way which shows both amplitude as well as phase being changed. Okay. And this sometimes is also called as, this way of writing s of t and realizing this signal s of t is sometimes called as QCM, called as quadrature carrier multiplexing. Why is it called quadrature carrier? Because one carrier is cos 2 pi fct, the other carrier is sin 2 pi fct, which for historical reasons has been called as quadrature, quadrature denoting 90-degree phase difference. Okay. So, this is about the expression for QAM. Let us look at some simple examples of QAM. Okay. and we were actually started looking at the example. We said that the complex symbol sequence AN can be plus B, JB, minus B and minus JB. What would be the corresponding sequence Cn for this? Cn sequence will be all B's, right? It is a constant, right? However, what will happen to theta n? Theta n will be 0, pi by 2, pi and minus pi by 2, right. So, this would be the sequence theta n, right. Now, if I plot this in the I and Q plane, right, this will be the complex I and Q plane, plus B will be here, this is plus B, this is plus JB, this is minus B and this is minus JB, okay. So, this is called as quadrature phase shift keying. Actually, why it is called as phase shift keying? Because amplitude here is constant, right. All these points are at the same distance from the origin, all these points are at the same distance from the origin, okay. Furthermore, the way in which you have to choose this B is not arbitrary. There is actually a relationship between this amplitude B and the energy of the signal, right. So, go back to this S of t signal. Here you have square root of 2 Cn g of t minus nt. For the quadrature phase shift keying, Cn will be constant and it will be equal to B, right. If you evaluate what is the energy of this signal, or if you evaluate what is the average energy of this signal, you will see that the average energy of this signal will be 2B square, because each of them are at the same distance, and remember the energy is basically mod of the point square, right. So, these are the 4 different points in the signal constellation. The distance from each of those will be the magnitude square. This is the length squared that we talked about in the last module, right, about the geometric representation of the signal. So, the energy associated with this one is B square or mod B square, this one is mod B square and mod B square. Assuming that all these signals are equally likely to occur, and this 2 is because you have a square root of 2 here, okay. So, the amplitude would actually be square root of 2 into B, therefore, the energy is 2B square, okay. B is a real number, and then since there are 4 possible symbols and each of these symbols are equally likely to occur, we have assumed that one, this would be the energy, okay. So, this would be B square by 2, and if we want to normalize this energy into 1, right. So, if we want to normalize this energy to 1, we then have to choose B is equal to square root of 2, is that correct? So, we have obtained B is equal to square root of 2, or maybe I have made a small mistake somewhere, because what I was hoping to get is B is equal to 1. If I look at the energy here, each of these has an energy of 2B square by 4. Anyway, so maybe that number square root 2 is wrong, you have to probably get it 1, but the point stays the same. What you have to see is that you have to have a maximum energy constraint, or equivalently, if you say that the laser can only give you 1 milliwatt of power, right. So, you are constraining the maximum power that the laser can provide you, and then say to represent this plus B, I will use the full power PS. In terms of field, it becomes square root PS. This would be plus J square root PS. This is minus J square root PS. This is minus J square root PS. Sorry, this is minus P square root PS. That's all. Okay. So, this is minus square root PS. So, I have a constant power or the maximum power constraint for this. So, how do I represent this QPSK signal, or how do I realize this QPSK signal using an optical modulator? Start with the laser which produces your carrier, and then put a phase modulator. Because this is a QPSK signal, you can think of this QPSK signal as actually 2 BPSK signals, okay, and then have the output, okay. I have the sequence AN which is complex that is coming out here. I can split this complex sequence, which is that minus B, these components can actually be written in terms of the corresponding bit sequences. So, let us say this is 0 0, 0 1, 1 1 and 1 0. This way is called as gray coding constellation. So, this whenever you transmit this amplitude of plus B, you are actually transmitting the bit sequence 0 0. Then you have 0 1, 1 1 and 1 0. what you can observe is, if you look at the MSB here, the MSB is this fellow 0 and 1, they are on the opposite sides, right. Similarly for the other case also they are on the opposite sides. So you can actually employ that fact, and whatever that complex symbol AN you are getting, you can split this into two portions, okay, one corresponding to the MSB and one corresponding to the LSB. So this is the MSB portion and this is the LSB portion. You feed this in such a way that the phase modulator is operated in 0 and pi by 2, whereas this one is operated as 0 and pi, okay. To operate a phase modulator at 0, you have to send in 0, right. To operate the modulator at pi, your amplitude should be V pi. To operate 0, you have 0. To operate pi by 2, your amplitude should be V pi by 2. So the sequence that you get here, the MSB sequence and the LSB sequence, you can utilize this, I mean you can scale up the sequence values by 0 V pi or 0 and V pi by 2, such that the overall signal what you get is square root of Ps cos omega st plus theta, where theta is equal to theta of the first phase modulator and theta of the second phase modulator. What possible combinations can I have for this? Well, if the MSB bit is 0, then the first phase modulator produces 0, the second one produces 0 and pi by 2. So this will allow me a total phase of 0 and pi by 2, giving rise to the two constellation points, okay. Next, if theta Pm1 produces a pi phase shift, then I have two additional operations, I mean two additional phases 0 and pi by 2. Pi plus 0 is pi, and this is 3 pi by 2, which is actually equivalent of minus pi by 2, right. I get these two constellation points with two phase modulators. I am able to get the all 4 points and therefore completing the QPSK transmitter. So this is one way of realizing QPSK transmitter. We will see one more way of realizing QPSK transmitter in the next class. So we will talk about that in the next module. Thank you very much.